All right, so I'm going to start with what happened when I was at Caltech. So I went to the interviewed for a fellowship of some sort, and I said, "What do you want to do?" And I said, "I'd like to solve AI." And he said, "How?" And I was like, "Well, you know, I'll use parallel learning algorithms." And the guy said, "No." He said no in a very strong way. And okay, so this is kind of that was sort of bracing, and that would be unfortunate if he was wrong. But at the time, at least, I don't think he was wrong. He was actually right. People had not done parallel machine learning in any kind of effective fashion. Typically, what would happen would be somebody would try to do something with parallel learning, and then somebody else would come up with a better algorithm, and then yeah, so the better algorithm would not be parallelized, and it would still be faster, getting you to a better solution. Okay, so that was kind of unfortunate. And now the question is, why is it really hard? And I think that it's really hard because your first instinct is to try to create kind of a super scalable algorithm. So you take you have two basic objects here. You have the data that you want to train with, and then you have the model that you want to train. So you want to parallelize the model, and you want to parallelize the data, and then you want some sort of protocol for talking between these two. And so sort of the parameter server approach is kind of the first pass people come up with. And what you discover when you look at this is that it doesn't actually work that well. Okay, so the archive paper is one that I did a long time ago. That was my first experience with this. And then the Dean et al. Paper is a very well publicized paper at the time at NIPS, where they had this disbelief algorithm that they were and system that they were working on. And you don't hear about either of these days, right? So these are not the algorithms people use these days.
So these algorithms basically distribute the model and the data and they're synchronized somehow.
Mm-hmm. Yeah. So and you know, approaches vary. So if you're doing a parameter server in the disbelief style, you have essentially key value stores that are sitting there, and the individual machines will go and query for all the values of the weights they need, and then they'll have some protocol for when they update. The paper that I worked on, what would happen was you partitioned the data, and then the individual data shards would actually send their piece of the data to the model shard. And then they would compute, a partial prediction from a model, which would then be reassembled on the data shard side to figure out what the update was that you would then send to. Okay, anyways, didn't work very well, and neither of these actually worked very well. And that's kind of a pretty strong statement in the case of the Dean et al. Paper, because this was a team of 30 people or whatever working on it. This was Google's default big learning system for a few years.
So what do you mean didn't work?
Well, it's no longer around, and there's good reasons for it not to be around. It was a major effort that went nowhere, and the current systems do not look at all like these systems. Okay, so the question is, why did it not work? And I think there's sort of two critical issues that came up. So these are kind of overwhelming in practice. One of these is that they're dramatically inefficient. So the process of communicating, particularly back then, but even now, is much more expensive than the process of essentially communication with your own RAM. And so the process of communicating between machines has a lot of latency and a lot of bandwidth constraints, and that is a big problem. The other thing which comes up is it's really hard to get away from a non-deterministic algorithm here. So who here has debugged machine learning algorithms in the past? Right. Okay. So a few people.
Who cares? Given up on them and just.
Yeah. So machine learning algorithms in general are pretty hard to debug. If you have a non-deterministic machine learning algorithm, it is sort of nightmare to debug. That is a really killer issue. So if you change your features, do you get better performance? Well, yes, maybe you were lucky, or maybe yes because you're actually, or maybe it's actually worse on the expectation, but you just, because of random fluctuations, it didn't seem to work better. And particularly when you have these deep learning architectures where it's hard to believe that you're actually reaching a global minima. It's really hard to tell what happens or what the effect of something was on top of the non-determinism.
But it is true for like normal algorithms as well, like not the ones which are distributed.
That's true.
Like there is this inception network people haven't been able to replicate it for a long time.
Lack of replication may not quite be the same thing in general, but
I mean, I think the best I've seen people do is just like run it three, 4 times and report mean and variance.
yeah. So when you have these non-convex representations, you don't reach a global minima, but you can still have determinism because you can use a pseudo-random seed to initialize things. So that is not as good as just always getting the same solution, but it's still dramatically better than, some server that you don't even know about was talking on the network at the same time your learning algorithm was running, and so some packets from some of your servers were slowed, and so you got a different kind of performance profile, right?
But you can enforce ordering by numbering packets somehow and have those rules there. It's sort of in a very nasty, hacky way get rid of this problem.
Yep, you can. It kind of works, and so what I'm going to talk about is what people are actually using these days for learning, which is not quite as general as you might imagine here, because typically what happens is the model fits on a machine without the model being sharded across things. So if you're in a situation where you need to, your model's just too big to fit on a single machine, then you're going to force into this sort of parameter server view of things to some extent, and then maybe you want to start doing these hacky things, but it's not really what's being used. That's not how people train ResNet or whatever these days. I shouldn't say it's not what's being done, but it's not what's typically being done. The most common kind of learning is not of that flavor. Okay, so back in 2011, I think we had the first instance where I could actually defeat this interviewer that I had. So there was an ad data set. So the goal was to learn some sort of linear learner. So you wanted to just predict, given features, what the best prediction was for the probability of click. So there are 2.1 tera features, and what I mean here is sort of the non-zero entries in the data matrix. This was in 2011, so that was kind of a lot of data back then. It's less impressive now, but it's still a fair amount. It wouldn't easily fit on the disk. Okay, so the question is, how do you actually learn a good linear predictor? And some details here. So there are about 17 billion examples. There were 16 million unique features. So I'm distinguishing between sort of the non-zero features and the unique features. So 2.1 tera, 2.1 times 10 to the 12 is the number of non-zero features in the data matrix, while 16 million was the number of unique features. We were running in a Hadoop environment, so we had about 1,000 nodes. And the question is, how long does it actually take with a good algorithm to train? Any guesses?
You're asking.
Any wild ass guesses?
1 hour.
1 hour. Yes, indeed. Okay, so if you work it out, this worked out to about 500 million features per second. So you just take the total training time, the total data set. This is a multi-pass algorithm. We're getting to, essentially the final solution. So 500 mega features per second is faster than the I/O bandwidth of every machine. So the individual machines there had a gigabit Ethernet port, and a gigabit cannot push 500 million features per second. So that means it's actually faster than all possible single machine linear learning algorithms. And that means it's kind of no longer possible for somebody to come up with a more clever algorithm and succeed faster on that hardware. Right, so you cannot push the data set through a single machine in that time. So this is the first instance I know of where that was achieved, where you could actually say parallel learning is necessarily doing something for now and for the future as people invent better algorithms.
How does it perform?
It gives you essentially the best linear predictor.
Okay.
So if your goal is a linear predictor,
Mm-hmm.
which is a caveat to some extent, then this gave you about the best you could possibly hope for.
All right.
Okay, so how did this work? So the key was to use, so who knows MPI? Anybody know MPI here? Message passing interface. So MPI was the standardized API and library for high performance parallel computing. And inside of this library, there's an operation called AllReduce. And I'll show you what happens with AllReduce. So every node starts with a number. That's the beginning state. And the end state is every node has the sum of all numbers. Right? So you're running through your code, you call AllReduce, the same AllReduce call happens on all the different machines, you feed in the number, and then the output, once the AllReduce call ends, you have the sum of all numbers. So this is a barrier that synchronizes the state across different machines. Okay, so now the next step is how do you actually do AllReduce? And there's actually several ways to do it. I'll show you a simple way to do this, which is what we implemented, but it may not be the best way. Okay, so the simple way is you create a binary tree over your nodes. And then to do the AllReduce, you have the leaves kind of propagate their numbers to the node above and do the addition as they go. Right, so 1, 2, and 5 become 8, while 3, 6, and 4 become 13. And then you do that as another step. 8, 13, and 7 become 28. And then another step, you propagate down the individual things, right? So there's a combination of kind of a reduce and a broadcast built together.
Why not just have like all the nodes send it to one master node and the number back?
Yeah, so if all the nodes send to one master node, then the bandwidth required for that master node is going to be proportional to the number of machines, which is kind of unfortunate in general.
Is this sum of all numbers just an example, or why are we summing up all the numbers, I guess?
You can use any reduce operation.
Okay.
And in general, in the library that's in VW, it's templated, so you can template with any function that you want.
Okay.
The sum is what we actually did at the time, and it's a good example. It's a powerful enough primitive, just that one, to do something pretty useful in machine learning.
Okay.
Okay, so I think the question is, what are the properties of this? What makes this a good primitive?
So what did you do? Did you sum the weights, basically?
We'll talk about how we use it in a minute, but let's just talk about the network properties of this for now.
Okay, so one more question about
Yeah.
that. So at the end, all the nodes, by definition of the AllReduce, have to be the same state?
Yes.
Okay.
So it's a state synchronization system. Okay, so trick number one is you can pipeline this. So if you have a vector of numbers to AllReduce, instead of calling AllReduce on each individual one, which would be very slow, you can call AllReduce on the array. And then when the array is propagating up, it may be that some parts of the array are still getting summed at the interior node, while other parts at the beginning are getting summed at the root. So you can pipeline the process of moving up and down the tree. And that means that the latency of the links, the latency of sending data from one machine to another, is kind of hidden by the bandwidth, the size of the number of the vector. So let me say this a different way. Modern hardware can communicate and compute at the same time. So you can have your Ethernet card and your CPU sending and receiving and computing all at the same time. And you can take advantage of that by pipelining everything. And you can pipeline all the way through from the top to the bottom, or vice versa. Okay, so that's one thing. Another thing is that the bandwidth here is essentially a constant per number that you want to add up. So n here is the length of the vector.
Why is it 6?
So when you have an internal node, let's go here. So for an internal node, let's think about the 5, okay? The internal node takes 2 inputs and gives you 1 output going up. So that's 3. And then there's 1 coming back down when it gets to 28. And then there's 2 more going back out. So you can account for this in several ways. You can say, oh, there's 3 sends and 3 receives per number. Or you can say, and maybe that's the right thing because you can overlap them entirely. Or maybe, yeah. So for optimal approaches, you don't actually have 6 or 3. You can actually get down to, I think 1 if you have overlap, send and receive.
Oh, yeah, so that's one thing. So while these nodes are doing computation at the bottom, the top nodes are empty and like wasted.
Yeah.
So once you're going up, can you just like put the parent as one of the child, which is no longer doing any job? So you can kind of reuse.
Let's hold that thought for a little while. But yes, there's a lot of other ways to do AllReduce as well.
So you didn't use a branching factor of 2.
You did actually.
But so that's kind of weird because the bandwidth of a node, you can use more of the bandwidth if you added more children.
Using the bandwidth is not the problem. It's minimizing the use of the bandwidth which is the problem. Right. So if you have a branching factor of 3, then you have 3 inputs coming in, which takes 50% longer than 2 inputs because we're doing this. We're going to be doing this on 16 million dimensional floats.
But your tree will be significantly shallower.
Yeah, it's all logs, right? Log base 2, log base 3. It's not that big of a difference. The key thing here is whether or not you have a logarithmic depth, because that means that the latency is just going to be the latency of a link times the log of the number of nodes, which is hidden by the number of bytes you need, the bandwidth capacity, basically.
Okay.
That was a philosophy, at least. Okay, so how do we do this? Here's an example algorithm. It just runs AllReduce on 1 to get the number of nodes, and then it runs AllReduce on the weights to average the weights together. And then, well, okay, you get the sum of the weights and then you just average them. Okay, so that's simple and easy enough. There's a lot of other ways to use AllReduce in parallel algorithms. You can do non-uniform averaging. Essentially what happens there is you average, you do AllReduce to figure out how you want to average, and then you do AllReduce again to do the non-uniform averaging. You can do conjugate gradient, you can do LBFGS, you can do, later on we'll see, you can do AllReduce for mini-batch gradient descent. So if you have a subset of your data and you want to compute the gradients and then synchronize on those, that's fine.
I mean, these are kind of operations which can't be done in this way. I mean, I assume there is some underlying property, which is like you can break the problem into smaller problems, solve it, or did I miss something?
There are certainly things you can't do with this, but I think the claim is that this is a really useful primitive that is sufficiently powerful for essentially all learning algorithms.
So adaptive gradient will be harder.
That's implemented. That's the non-uniform averaging. So we do AutoGrad with AllReduce.
Mm-hmm.
I think your question is like, then you have to maintain the square of gradients, and you have to like constantly synchronize it.
Yeah, so there's a question about how you want to actually synchronize the sum of gradients squared,
Mm-hmm.
right? And I forget, are we doing a non-uniform weighting? Are we using the max? One of those two.
So approximation. Okay.
So anytime you're doing any kind of weight averaging, you're doing an approximation of what would happen in the true online setting, because
Mm-hmm.
you're learning without the updates that would have been incurred by other examples and other nodes, right? And we actually do see that experimentally. And the rate of convergence as a function of the number of passes goes down.
Mm-hmm.
You need more passes to converge. But still, if you're working with 1,000 nodes, it ends up being useful.
Okay. I'll put out the order for 1,000 computers.
Yeah. So you really need to have one of the big clusters available to play with this. Okay, so are there questions about this? So there's a notion of statistical query algorithms, which I think is a good notion. This is from theory. The claim is that a lot of learning algorithms can be thought of as computing a stochastic average of some function. And stochastic average is exactly something that you can do with AllReduce. It's very natural to do. And that means that any statistical query algorithm could be done with AllReduce. Okay, so we made this work in Hadoop. And I think Hadoop is a little bit less relevant today than it was 6 years ago. But it's still fairly relevant. So Hadoop has a bunch of systems. Okay, so I guess working with Hadoop meant two things. One of them is we could not use MPI because Hadoop likes to control the cluster and MPI likes to control the cluster, and they don't mix very well. The other thing is that Hadoop had various primitives that we wanted to use. Right, so Hadoop distributes the data. So the data resides in different nodes. And then it kind of moves the program to the data rather than vice versa. So that's very useful. Another trick which comes up is often one of these nodes fails for some reason or another. Maybe the disk fails. That was kind of the most common thing that we saw. So even if you try to use MPI on Hadoop, because MPI set up the communication network at the beginning of the computation, as soon as one of the nodes died or just was incredibly slow, the entire computation would sort of fail. So that's in general a property of even this AllReduce, but we managed to make it much more robust because we could delay the initialization of the communication infrastructure until after every node had gone through its own data once. And then you can go through the data and you can cache it, and then you can kind of be sure that the node is working functionally in a good way.
I mean, there are these algorithms for like these adversarial settings, like Byzantine kind of failures and like that. So,
yeah, those are generally not terribly efficient. Okay, so you go through, you kind of exercise each of the individual nodes of the computation, and then you establish the communication. And what this meant was that if a node failed in that initial exercise, Hadoop's kind of auto restart mechanism would, restart the same job, the same process on the same data on a different node. And then when that one completed, you could do the overall computation. Okay, and then the last thing was people had dealt with this kind of issue before in Hadoop, so they also had a mechanism for doing speculative execution. So if some particular node was going slow, not necessarily failing, it was just slow, they could restart the job on the same data, and then you could race between the new and the old one to see who finished first. So these are the kinds of tricks that we had to deal with in order to make this be kind of work reliably in Hadoop. So in the end, what you get is something which kind of gives you the best of MPI and the best of Hadoop, while taking advantage of Hadoop's primitives. I would say, though, that Hadoop is not a really great environment for doing parallel learning. And the problem is that you have a machine that has maybe 16 cores. You're going to take one of the cores with your job. There's going to be up to 15 other jobs running on the same machine. And the way that those other 15 jobs hit the disk or force things to swap greatly affects the speed of your process. And then there's kind of an issue because you have to worry about the slowest process. So you have 1,000 nodes, you have 1,000 pieces of data. If you're training on each of the 1,000 pieces of data, the slowest one is going to be the one which limits your speed of completion. And now, how fast can you be when it's the slowest out of 1,000? And the answer in Hadoop is it can be pretty darn slow, because those other 15 jobs in the same box can really affect your performance. All right, so using these kinds of tricks, we managed to get out to about 10,000 node hours. So what you get when you, so here what we're looking at is the speed up that we get compared to linear. So we're going from 10 to 100 nodes, and we did 10 different runs. Linear would be ideal. That would be what you would hope for. In practice, very difficult to achieve a linear speedup, or rather, I should say, if you achieve linear speedup easily, you probably have a really bad baseline algorithm. We have a pretty good baseline algorithm, so achieving linear speedup was not really possible, but we could get something which is vaguely near to linear.
Wait, which is the performance of your system?
What's that?
Which of this line is performance of your system?
So this is, we run the same job 10 times, right? And we're just looking at
Average.
How does the performance when we have 100 nodes, what's the speed up with 100 nodes compared to what we have with 10 nodes? And what we see is a factor of 7 speed up on average, varying but between a factor of 6 and 8. Right.
So this is for the linear feature algorithm.
What's that?
This is for the linear feature algorithm.
Yeah, just doing linear. It's VW, running both at 10 nodes and at 100 nodes, right? Okay, so it's kind of fun. We applied this to some big data sets. The Splice site data set is a public data set. This is trying to find Splice sites in DNA. We found that on these big data sets, it was often useful to start with online learning and then switch over to LBFGS. And I think we haven't really had time to talk about LBFGS in particular. Online learning we have talked about. LBFGS is a batch learning algorithm which can get at second order structure. So what does that mean? It means So the gradient might be very high in some directions and might be relatively low in other directions. And if you're just doing gradient descent, you're going to make a really big step in that high gradient direction. But it can easily be the case that you rattle back and forth if you're taking the high gradient direction, while in the low gradient direction, you actually make steady progress. So a second order method will get at that kind of improvement. So anyway, what we found was that LBFGS was sometimes helpful as a second pass. So if you started with LBFGS, then it would take forever for it to convert to something useful. But online learning would kind of initialize LBFGS pretty well, and then you could use LBFGS effectively. All right, so we compared with some other algorithms of the day. The Zinkovich et al. One was an algorithm where they took the data, and for every node in the computation, they had 1/4 of the data. So there was a lot of data per individual node. So you kind of create a very overcomplete partition, and you would train on each overcomplete partition independently, and you just do one average at the end.
That works.
I mean, you can see it didn't give as good a performance, and it was each of the blue line and the red line were substantially worse computationally than. This is just talking about the prediction performance, but computationally they were more difficult. It does kind of work under some assumptions, but I think it doesn't work in practice basically because the requirement that you have 1/4 of the data on each node basically means you can't apply it to a large data set.
No, I mean, I'm more concerned about this, like averaging, like separately training and then averaging.
Yeah, I think the idea is that if you get enough data and you're averaging in enough ways, it kind of works out. There's some theory. I don't know if it's particularly insightful, but that's the rough idea. The other one was with Dekel, was doing mini batches to average. And I guess the observation here was that that was incredibly slow. So there was a lot of compute hours in that red line, about 40,000, which was something where the computation could easily fail for one reason or another in the process. So mini batch averaging did not work very well in a Hadoop environment, particularly because of this exogenous load problem, right? So individual machines might be loaded in very different ways, which meant that the computation became very slow. Okay, so this is, I think, the first time that AllReduce was really talked about in machine learning, and this was the first case I know of where you could really show that no future development in algorithmic quality, if your goal is linear learning, would actually give you something which is more performant on that hardware. But since then, a lot has happened. And in particular, people have been playing with GPUs a lot and with deep learning a lot. And so I think it's good to think about and know what's going on as far as parallelization there. Okay, so the first thing is GPUs themselves are parallel. And so inside the GPU, you're doing a parallel computation in a very SIMD fashion. So you have a single instruction, multiple data, so that the same things get executed on different pieces of data over and over again in order to do these computations. So programming a GPU is not great fun, but people have created various libraries now which do the programming on a GPU for you. And so you can actually train pretty powerful models relatively easily. The other thing which I think is very nice about a GPU is that it's dramatically more efficient than this kind of computation. Here we're running on 1,000 machines. For a machine with a GPU, I think you should count it as being maybe a factor of 2 or maybe a factor of 4 more energy than a single machine here. So just in terms of the power draw required. So you pay a factor of 2 maybe going to a GPU-based machine and GPU-based computation. But if you're paying a factor of 2 rather than a factor of 1,000, then that's pretty dramatically useful. Because it's much more efficient in terms of the number of the amount of power required per flop. Okay, so the other thing is that's kind of remarkable about GPUs is that the ratio of communication to computation is different. GPUs do teraflop scale computation. So a modern GPU, I think, is about 10 teraflops. This one, I think, is about 4 teraflops. So on the other hand, a modern CPU is only about 1/4 teraflop. And that's if you know all the tricks for really trying to do assembly instructions that exist on a CPU. So there's a factor of 40 or so more computation going on in that GPU than on the CPU. And that means that, okay, so the communication between the GPU and the world is through the same interface as it would be between the CPU and the world. So you have a factor of 40 less communication per computation available. And that means that if you want to parallelize over multiple GPUs on different machines, you need to be much more refined than we were back in 2011. Okay, so there's a bunch of tricks people have developed for trying to do parallelization over multiple GPUs on different machines. I just wanted to go through those and show you them to give you a sense of what's going on. Okay, so one trick is related to mini-batch gradient descent. Now the good news with GPUs is that they're much more isolated. An entire process takes the entire GPU. There's no sharing of a GPU. And so the computational time required on a GPU is much more predictable than it would be on a CPU with multiple cores and multiple jobs running on those different cores.
I mean, you can share it. You can share it.
I
mean, I ran multiple processes on single GPU.
You ran multiple processes on a single GPU simultaneously?
Like TensorFlow allows you to specify the fraction of GPU memory that it would use, and you can specify that you can run as many of your processes.
So maybe it's
So that was certainly not available back in the day earlier. So I guess my knowledge here comes from about 4 years ago when we were playing around with creating GPU racks. And there was the case that the GPUs could only have one outstanding input or output request at a time, which kind of meant that
it doesn't contradict it.
Okay.
So you can allocate, you can say memory is allocated here, memory allocated here, and then you just alternate between the different things, but keep the memory reserved to them.
That would be very slow.
It would be very slow. It actually, I mean, it will be slower than running on 2 separate GPUs, but because the memory is not swapped and you kind of reserved and distinguished, then it's not so bad.
Well, you didn't say communication and the CPU and the GPU, right?
No, it's like you basically you want only one process on the GPU at one time, but you alternate between them. But you keep this, but you keep their memory allocated for them. That's one way to do it without.
I see. Yeah, so, that would work.
Yeah, but it will be a bit slower than running on 2 separate GPUs.
I don't think that's happening because I don't observe this clocking performance, but could be. I don't know.
Well, your algorithms also have a lot of other things happening, so the GPU is not really.
Okay, so a standard trick for doing parallel computation on a GPU is to use mini-batch because you have much better isolation, and that means that the synchronization overhead is much lower than it would otherwise be. So you give every GPU in examples and you compute the average gradient on them. Okay, and then because the processes are better isolated, the synchronization is not as expensive as you might otherwise imagine. Okay, so that's one trick. Another trick is I've heard it called half batching. So here we're going to take advantage of the fact that hardware can communicate while computation is going on. So the idea is that you have 2 mini batches that are live at the same time, and One of them is alive in the sense that you're computing the gradient on that mini batch, and the other one is alive in the sense that you've already computed the gradient and you're just synchronizing the weights. And so that allows you to kind of use the communication and overlap the communication and computation.
So one mini batch is stale. You're working on stale.
Yes. So you're one mini batch behind in terms of staleness, but things are still deterministic, and so you can still debug what's going on. Right. So that's a minor improvement. Another trick is this 1-bit SGD. So this is something that Frank Seid cooked up when he was working on speech recognition. And the idea is that you need to communicate the gradients if you're doing many batch gradient descent. So that's expensive because it's like a float for every single parameter. So instead what you're going to do is compute the average on the GPU. We do that anyways. And then you discretize it to 1 bit. And then you keep the residuals around the error in your discretization. Okay, so when I say discretize to 1 bit, may not be clear enough. So the gradient is some real number, and it has some range. So what we're going to do is we're going to draw a random number. Let's say the gradient is between 0 and 1. So let's say the gradient is 0.5. Then with probability 0.5, we'll say, oh, the gradient is 1, and with probability 0.5, we'll say the gradient is 0. Or let's say the gradient was 0.25. So then with probability 0.25, I'll say the gradient is 1. With probability 0, for probability 0.75, I'll say the gradient is 0.
But then you're not deterministic anymore.
What's that?
Because you're sampling.
No, it can be, there's no true random number, there's just pseudo-random seeds.
Okay.
Okay, so then you have your discretized value and you have your true value, and you keep track of the difference on the GPU. But then you communicate your discretized value, which is now at a single bit level, through an optimized AllReduce.
What's the drop in performance?
What's that?
What's the drop in performance on discretization?
Pretty near nothing. There's a paper about it. It's in the references. You don't lose much doing this.
So your final model is only integers?
No. It's more complex than that.
I was hoping.
So you keep these discretization errors on the GPU, and then and then you that feeds into the next mini batch basically.
All right. So it's not like it's not just you giving a 0, 1, 0, 1 gradient.
Well, I mean, the averaging itself, the averaging process itself does result in something which is not 0 or 1. Right? If you're going to average across all the mini batches which have been discretized,
Sure.
it's something which is not so discretized when it comes back to the GPU. Okay, so this is a real gymnastic that people do, and this actually does give significant scaling benefits. And then Baidu had this ring-based AllReduce, which they really like. So they have a highly optimized AllReduce implementation. And here the communication pattern is different. So this is related to your comment earlier. So the idea is that there's a ring over all of your nodes, and the communication will be going through that ring. Now, this would be terribly slow if it wasn't pipelined, but you are going to pipeline it. And furthermore, you're going to start the pipelines for different parts of your vector that you want to synchronize on different nodes. So node I will begin the ith portion of the pipeline, and node J will begin the jth portion of the pipeline, and so forth. Right? So you partition a vector, and then the first node takes the first part of the first partition, the second node takes the second partition, and so forth. Each of those begins communication along the pipeline. And in the end, what you can show is that this approach gives you bandwidth optimal AllReduce. Okay, so it's perfectly efficient in terms of bandwidth utilization. In terms of latency, I think I'm a little bit worried about this in terms of latency because you still need to go all the way around the loop in order to finish the AllReduce operation. And that means you have to add up the latency of each of those links.
I mean, in this case, it's the training data split into 5 disjoint sets, and each GPU has access to one of the sets.
Yeah. So I think at 5 nodes, this is fine. I don't know, at 1,000 nodes, this would be fine. I think,
So these are also running on the same machine.
no, not necessarily.
Okay.
But the GPUs, the modern GPUs do support direct GPU to GPU copies. So you can do a copy from one GPU to another on a different machine over the network without ever touching the CPU.
This is not a regular network. They have this specialized. It's not. I don't think it's regular Ethernet. I remember.
Well, once you start playing with GPUs, you don't want to work with Ethernet anymore, anyways. You want to work with InfiniBand, which is a much better protocol for latency-sensitive communication.
I mean, so when people say this is a GPU cluster, what do they mean? They mean like there's a room filled with like 30 GPUs right sitting on a single board, or what?
No, a GPU cluster is typically made out of individual machines which have 2 to 8 GPUs and are connected by InfiniBand internally.
We have so we have one GPU cluster, the Facebook one.
I mean, Amazon also has these machines.
Well, Amazon there.
Oh, yeah, but they have a machine.
Well, I think single machine is, I mean, that's fine. But if you really want to try to work with some of the bigger data sets people try to work with, parallelization is really nice. I mean, if you're spending 2 weeks training, getting that down to a day it's good.
I mean, the Amazon machines have like 16.
What's that?
8 or 16 GPUs. It's quite a lot.
16 GPUs on a single machine, or?
I think so. I don't know how Amazon
do that.
I've only heard of 8 on a single machine.
So, but these are virtual machines.
Yeah, I mean,
So I don't know exactly how they're structured.
Virtual machines, you have to be very careful about the.
But in AWS, you can get an instance with 16 GPUs.
Okay.
What does it mean physically is a different question.
And you can try to measure that by timing latencies between them.
Yeah, below 6.
Okay, so and Baidu put out a library with the Ring AllReduce, which is available. I think they made that work with TensorFlow even. So that's kind of where we are as far as parallelization on GPUs. So presently, I think AllReduce is kind of the standard primitive for doing parallel learning. And in addition to what I talked about, I think I missed something. You can make it work in various ways. The other thing which is really nice is that it doesn't impact your code very much. And so you don't have to refactor your algorithm in order to parallelize. You just stick an AllReduce in it at strategic points, and then the code works in parallel.
But you have to define the reduce function, right? And the reduce function has to be stateless.
Yes.
It has to be a lambda.
Yeah.
That's kind of requires restructuring in general.
Well, I mean, if you're doing mini-batch gradient descent, you can just use sum, like we talked about here. It's not a difficult lambda.
Yeah, I mean, once you're working something complicated.
Sorry, I was going to say, so if I'm understanding like this, how this works correctly, you would have some number of machines, and each one would have a certain set of data. You like run each machine on that set of data, and you get some gradients, and then throughout the entire system, you average over everything, and then you can continue running different like instances of the model. It's just that now you've updated the weights so that they're all the same across each machine.
So there's several variants. One variant is when you do AllReduce on the weights, and then at the end of the AllReduce, the weights are the same. The other variant, which is very common, is when you do AllReduce on the gradients.
Okay, yeah.
And then you have the same gradient on all the machines, and then you do the same update on all the machines.
Right. Okay. But you do have, n copies of the actual instance of the model that's running.
That's right. That's right. So if we go back to the beginning or near the beginning, this is not the picture. because it's more like a full instance of the model is running on with each data shard.
Okay, yeah.
And there are a few people who work with models that are larger than a single machine, but I think that they're not very commonly used or not used very effectively. Those models are of a scale that they're kind of unwieldy enough to train that they just haven't been that effective so far. Also, I think RAM in general is increasing, so it's kind of a race, right? So if you're working on models which are too big for RAM, you have to keep increasing the size of your model in order to deal with the fact that RAM is increasing.
Also, I've only worked with one GPU at a time, but I know that people sometimes have to work with multiple, like if you have some softmax over like hundreds of thousands of outputs, right? So in that case, how easy is it to just like add and I know this is not exactly the same thing, but how easy is it to put your model on multiple GPUs? Is this trivial or I don't know? I mean, this is not entirely related, but.
I mean, in TensorFlow, it's very easy.
Oh, okay.
In TensorFlow, you can specify the device ID for a given operation. So you can say this part use device 0, this part device 1, and then the TensorFlow does a mapping like device 0 to GPU 0, device 1 to GPU 1.
Oh, okay.
So you can explicitly.
So that's distributing them. That's sharding the model, basically.
Yes.
Right.
That's also sharded updates because you need to protect those too.
So.
That's really clear.
I haven't worked with TensorFlow very much. Truth is, I haven't worked with GPUs very much. I understand that in CNTK it's relatively easy to do kind of the so you have mini-batch gradient descent with half batches using 1-bit SGD with an optimized AllReduce, right? So you can if your model fits onto a single machine, then you can run pretty effectively on lots of data across many machines and converge to a good solution. For distributing the model, I guess I am curious how well it actually works.
I'm not 100% sure that's what they do. I mean, they're definitely running ops separately on different GPUs, but maybe they also share the model, like the same model, but they tell that operate this ops on different.
So in general, the scheduling of communication across the GPU interfaces is extremely non-trivial. And it can be, if you're allowed to specify that this op runs on a different GPU from that op, then it's very easy to create a communication pattern which will overwhelm the interface.
I think the case that Aline mentioned is one where only alternative which I'm familiar is just not. Like you're working with a vocabulary which is like 100,000, and you just the matrix will either won't fit on the single GPU, or if you try to do it, it just takes a very long time. So I mean, I'm sure there's a delay, but the benefit out of it.
I mean, in these cases, the delay actually can be very slow because this happens at least during inference, because this matrix multiplication is at the end of the prediction, and you can just take the max from each of your, they call it towers, from each of the different pieces, and then it's like 1 bit you have to communicate and do the max between them. So that's actually trivial. Learning is much more. Learning is also not that. I think it's a bit more tricky actually. Yeah.
So I think you have to communicate is just like probability.
For what?
So it's just for the vocab. Like
So forward that.
Yeah.
Yeah.
Okay, so I had some bibliography notes. So LBFTS, which we did not have a chance to go through, something that I went through in a previous class at NYU 4 years ago. So that lecture is still online if you want to look at that. There's a bunch of papers in roughly chronological order about developments of AllReduce, online learning, parallel learning. And then this one is, I think, where the more modern algorithms are. So the Terascale learning one was late in 2011. The disbelief was in late 2012. The 1-bit SGD was in 2014. And then the ring AllReduce as applied to speech recognition was in ICML last summer. Okay, so we're essentially done with the class. I thought that it might be kind of fun to look back at the beginning of the class, just for a minute. All right, so there's machine learning in the present, which is supervised learning. There's a lot of advanced applications we would like to actually get at. We've kind of discussed some elements of these. There's a lot of many that you would like to do. Just thinking about what is necessary for success. There's what pieces do you need to solve. So we discussed online learning. We haven't had a time to go into representation very much. That's a big subject in general. We spent a good bit of time on reinforcement learning of one sort or another. We talked about exploration. We haven't had a chance to talk about language very much. Reasoning, we haven't had a chance to talk about. Memory, we haven't had much of a chance to talk about. These are all good subjects, which I think could easily fit into this class, but yeah, I got sick and I wrecked my face and things like that. Okay, so then what we did talk about, I think, is actually represented pretty well here. So there's sort of supervised learning, which is the red. And then if we look through the different algorithms that we went through, it's everything which is kind of intersecting with supervised learning. So we talked about active learning, contextual bandits, contextual decision process, and policy improvement approaches a fair bit. Okay, so that's the class. Are there any questions, comments, thoughts?
What do you think about the asynchronous method of DeepMind, where they have like these different agents which have a model at a given time, and they are generating experiences. These experiences go to a parameter network where they do like these.
So I think gathering experience from multiple agents is pretty desirable in general. So one thing we didn't talk about for the active learning, there's a paper on archive that we never published called para-active learning. But the idea is that you use active learning approaches to gather the information needed to train. So it's kind of like a parallel search for the information that you need in order to learn effectively. And this sounds like it's kind of a para-active style approach. Okay, thank you.
Thanks, John.
Yeah.
Thanks.